see it, then go. Huh? So, this is in continuation of our previous lecture. We wanted to discuss the various properties of the continuous functions, and as a consequence of that, we see that if function is continuous over a closed bounded intervals, then we have some results which is known as the boundedness theorem, maximum minimum theorem, and the Bolzano's theorem, and this gives you the also a criteria to find out an approximate solution for the root of the function, that is root location with the help of this. Okay. So, let us see first what is the bounded. Before going for the boundedness theorem, I will recall the definition of a bounded function. Bounded function, we define like this: a function f from a set A to R, where A is a non-subset of R, non-empty subset of R, is said to be bounded on A if there exists a constant m greater than 0, such that the mod of f x is less than or equal to m for all x belongs to m. It means a function is said to be bounded if the corresponding range set is a bounded set. So, when we say the f is not bounded, it means that is so a function f from A to R is not bounded. It means we are unable to get such an m for which this inequality holds, or we can say that if given any m, then a function f is said to be unbounded. Then if given any m greater than 0, there exists a point x which depends on this bound m, point m belongs to A, such that the value of the function at these points will be greater than the desired the given number m. So, whatever the number you choose, you can always find a corresponding point in A for which the functional value will exceed by that number m. Then we say f is unbounded or not bounded on the set m. Okay. So, this is we have already discussed. We wanted now the result, the theorem which is known as the boundedness theorem. The theorem says let I be a closed bounded interval, and let f be a function from this closed bounded interval to R, be a continuous function, on I. Then this theorem says f is bounded on I. So, every continuous function on a closed bounded interval will be a bounded function. That is what he says. Proof. We will prove by contradiction. Suppose f is not bounded on I. Suppose f is not bounded on I. So, by definition we cannot find an m such that the mod of f x is less than equal to m. So, we can get then for any n belongs to natural number, there is a number x n in the set A such that the value of the function, absolute value of this functional value f of x n will exceed by n. So, corresponding to 1 we get 1 point x 1 in A, so that f x 1 is greater than 1, 2 we get f x 2. So, we get a sequence of the points in A which will satisfy this condition f of x n is greater than n. Okay. But since I is bounded, since I which is giving to be the closed bounded interval is a bounded set, and all these sequences x n which you are getting satisfying the condition say 1, satisfying 1 lies in A, in I, lies in I, because these are all the sequences belonging to I, and I is a bounded set. So, the sequence x n is a bounded sequence, because x n lies between A and B. So, that all the terms of the sequence have a lower bound say A, upper bound say B. It is a bounded sequence, and we know by Bolzano-Weierstrass theorem every bounded sequence has a convergence sequence. So, use the Bolzano-Weierstrass theorem. The Bolzano-Weierstrass theorem so use Bolzano-Weierstrass theorem. This will give, which gives a convergent subsequence x n k of say x n k of this x n, convergent subsequence of x n of x n that converges to the point x, converges to a number x, to a number say x, because by definition x n is a bounded sequence. So, Bolzano-Weierstrass theorem says, by Bolzano-Weierstrass theorem we can get a subsequence which is convergent and converges to a number x. Now, this x obviously belongs to I. Why? Because since x is x n k, all these terms of the sequence x n k lies between A and B. This is a closed interval, I is closed interval, all the terms of the sequence lies between this. So, the limit of this sequence x n cannot exceed between these, will always lie between these two bonds. So, since this is there where I is a closed bounded interval, so the limit point of this sequence x n k over k, this limit point obviously belongs to I, obviously belongs to I. Okay. But this limit point is x. So, this shows that x belongs to I. You know. So, what we get is that a sequence x n k has a subsequence which is convergent and the limit point belongs to I. Now, f is given to be continuous. Since f is given a continuous function over the interval I, and x is one of the point inside the I. So, this implies f is continuous at x. So, by Henny-Wheeler theorem, therefore, this implies limit of x n k when k tends to infinity is x will give you will give f of x n k limit of this as k tends to infinity is nothing but what? F of x, okay, because by the convergence part. So, what it shows? This implies the sequence f x n f x f x n k, this sequence is a convergent sequence. Is a convergent sequence, okay, and convergent sequence is always bounded. So, it is bounded. It is bounded, but that gives a contradiction to our result, because this sequence f of x n is greater than n. So, from here from 1, but from 1 what we get? We get mod of f x n k is greater than n of k, which is greater than k, of course, greater than k, and this is true for all k belongs to n, all k belongs to n. So, this continuous function is not bounded on the closed bounded interval. So, this shows that function f, this over this sequence. So, supposition that function is not bounded gives a contradiction. So, this gives a contradiction of our second part, but from we get this which contradicts 2, because here this shows this is unbounded, where we have already shown it is bounded. So, it gives a contradiction, and contradiction is because of our assumption that our function f is not bounded on I. So, this shows that function f is bounded on I. This implies f is bounded on I, that is closed interval. So, this proves the result which is known as the boundedness theorem. Now, in the boundedness theorem, we have assumed these conditions. What are the conditions in the boundedness theorem is? First condition is the interval on which the function is defined must be closed and bounded. So, this is one of the condition which we have taken. Second condition which we have taken, the function must be a continuous function on this. So, interval is closed, bounded, and function is continuous, then only we can say f is a bounded function on this. If any one of the condition is relaxed, that is, if we take I to be a simply bounded interval not closed, or simply closed not bounded, or function is not continuous, then our conclusion that f is bounded on I cannot be drawn. In fact, we will get a contradiction. We will get the example where we get this function is unbounded when we relax any one of the condition. So, let us see the examples. The condition note, the conditions of the boundedness theorem. The hypothesis of boundedness theorem is each condition of is needed to justify or to get the function f, to get a continuous function to be bounded on I. If we relax any one of the condition, then we get the conclusion fails. The conclusion of the theorem fails if any one of the hypotheses or if any one of the conditions of boundedness theorem is relaxed. For example, suppose I take the function, say function f x is suppose x, the interval I am choosing I as an interval is 0 to infinity, okay, and now this function is continuous function it is a continuous function on this interval I, but I is not that is the function is closed, but unbounded, is not bounded. It is unbounded one, though it is closed. Though it is closed, because all the limits point of between 0 1 are inside it. So, I is a closed interval, but it is not bounded. Okay. Then what happens? The function is continuous throughout, but the bound for this function, but function f x equal to x is an unbounded function, because as x increases, the value of the f x keeps on increasing and interval is up to infinity. So, it is without bound. So, it is unbounded, therefore, the conclusion failed. Second, if suppose I take the same function g x as say 1 by x, this function, and the interval I choose I to be the interval say 0 1. Now, this interval is not closed, but bounded. Function f x is continuous over the interval 0 1, because 0 is not included, but we have seen this function is also unbounded, as because as x tends to 0, the function g x will go to infinity, unbounded. Then, so again the relaxing the condition is again not going to help, that conclusion fails. Then if I take the interval I as a closed interval, which is a closed and bounded, okay, but now I am taking the function h x as 1 by x if x belongs to the interval say 0 1 and 1 if x is 0. I define this function. The function is continuous over the 0 1 interval, okay, but it is discontinuous at the point 0. Clearly, h is discontinuous at x equal to 0. So, again the conditions is not satisfied, and obviously clearly h is unbounded. H is when x approaches to 0, the this is not a bounded function. Okay. 1 by x for this 0 1 and 0 when it is discontinuous and unbounded on C. Okay. So, this will be there. Okay. So, we can see that in boundedness theorem is can only be applicable when all the three conditions are taken in consideration. The next result which we want to maximum minimum theorem. The maximum minimum theorem the theorem says let I be a closed bounded interval, be a closed bounded interval, and let f, which is mapping from I to R, be continuous. On I. Then f has an absolute maximum and an absolute minimum on I. This results. Now, we have already discussed the maximum, absolute maximum and absolute minimum in the last lecture. So, proof we go. What is the absolute maximum? We mean that if suppose a function is from a to r, then f has a absolute maximum at a point if there exists some point x star such that f x star is greater than f x for all x, and minimum when f x lower star is less than equal to f x. So, that is the way we have introduced the maximum of this function. We will discuss after this proof. So, suppose what we want is, suppose a be a closed bounded interval and function is given to be continuous, then it will attain its maximum value as well as minimum value over the interval I. That is, there exists some point where the absolute maximum will be attained, absolute minimum will be attained. So, let us see the problem. So, consider the set f of I, the set of those values f x where x belongs to I, means consider the range set of function f which is defined over I. Now, this range set, the values of f I is clearly bounded subset of R, and this follows, it follows from the previous, from boundedness theorem, because boundedness theorem we have seen, if the I is a closed bounded interval, f is a continuous function, then f of I, then f is a bounded on I, that is the range set will be a bounded set on I. So, it is a bounded subsets of R, this much we. So, once it is bounded subset, we can talk about the upper bound and lower bound and supremum of least upper bound and greatest lower bound. So, let us suppose S star be the upper bound supremum value of the function f I, and S lower star be the infimum value of the function f I. That is, least upper bound of the function f over the interval is suppose S star, and then. Now, what we want to here, this S star and small s star exist. It means there exists some function. What we wanted to prove, required to prove is that there exist points x upper star and x lower star in I such that the S star will coincide with the f of x star and S lower star will coincide with f of x lower star. This we wanted to show. So, first we will prove for this side and the other will follow in a similar way. Okay. So, let us assume so first to show that there exists an x star in I such that S star, which is the supremum value of f I, exists and equal to the value at this point. There exists. This we wanted to show. Okay. Now, since our x star, since S star is the least upper bound of the function f I, of the function f x for x belongs to I. When x belongs to the least upper bound of this function is S star. So, if I choose a number slightly lower than this, it cannot behave as a least upper bound. So, the number S star minus 1 by n, this number is a slightly lower than. So, is not an upper bound for it. So, is not an upper bound is not an upper bound for the set A or of the set f I, is not a bound. Therefore, there exist. So, we can say consequently there exists a number x n in I such that x star upper minus 1 by n is less than s star, sorry, this is s star minus 1 by n less than f of x n, which is less than or equal to s upper star for all n belongs to capital, because this is our upper bound. So, when you take a number slightly lower than this, then we can find a some number x n in I, so that the functional value of x n will exceed by this number, and obviously it will remain less than equal to this, because it is the least upper bound for this. Okay. Now, this sequence number x n, but this sequence is x n satisfying 1 are lying in the interval I, which is say a b, which is a closed and bounded interval, closed and bounded. So, by Bolzano-Weierstrass theorem, so by Bolzano-Weierstrass theorem, there is a subsequence say x dash, elements are x and say r, belonging to of x, of course of x is a sequence x n of x that converges to some number x upper star, say. Okay. Now, we want in fact this number which we have got it must be a point of a b. This we want to show first. So, how to show is, since all the elements of this are again the elements of I. So, since the elements of x dash, that is x and r, these are they belongs to I, which is closed and bounded interval, So, just like a previous thing, we can say, so just like previous theorem, we have seen that if the sequence of the point belongs to a closed and bounded open interval, then limit point will also belongs to it, and since it is closed, so limit point will. So, it follows from this that the limit point x star is also a point in I. Okay. Therefore, f is continuous at I. Therefore, f is continuous at this point also, because it is continuous throughout over the I. So, once it is continuous, so apply the definition, Haney-Weinreich definition. Haney theorem says if a sequence converges to x star, then f of x n will also converge, xr will also converge to f x star. So, by theorem, limit of f x and r when r tends to infinity coincide with f of x star, because it is continuity. But by the first one, use the first one. From first, what we get is s star minus n r is less than f of x n r, which is less than or equal to s star, is it not? So, this is true for all r belongs to n. Now, let r tends to infinity. So, this limit is s star, this is s star. So, by Eschew's theorem, the limit of this function f x and r as r tends to infinity will be equal to s star, but this limit is nothing but what? F x star. So, this implies there exists an x star belonging to I such that the supremum, because this is the supremum value of the function f I, such that this f x star is the supremum of f of I. exist, and that proves the existence of S. Similarly, we can show for that there exists a x dual star in I such that x dual star is the infimum of f of I, and this completes the proof for this. Okay. So, this is another results which you now next result is also interesting, that shows the location of the roots. Location of roots. In fact, this also known as the bisection method. Bisection method, it will be used in the bisection method for this, known as that the algorithm is known as the bisection method. So, we are not touching it. Okay. Location. What this result says is, let I be a closed and bounded interval, be a closed and bounded interval of R, and let f is a mapping from I to R, be continuous on I. Be continuous on I. Now, if at the point A is suppose negative, at the point B it is positive, or if at the point of A it is positive and at the point of B it is negative, that is at the corner point, if the function attains the different sign, then there exists a number C. There exists a number C belongs to the interval AB such that the value of the function at the point C will be 0. So, this shows that we can identify the root of the function if a function is defined over a closed interval AB, which has a alternate sign, that is at the point A is negative, at the point B is negative. So, there will be some point C where the and function is continuous. So, obviously, when the function is continuous, there is a continuous graph. So, when the function is negative, it means the part of the graph is below the x axis and part of the graph is above the x axis. So, obviously, because of the continuity of the curve definitely cross the x axis. So, that point where it crosses will be the point C, where f of C will be 0, and that is the shows the location. Now, proof of this is in fact, we will generate the sequence of successive bisection just like P. So, let us suppose I 1 is an interval, say A 1 B 1, okay, and assume, let us first assume that f of A negative and f of B is positive. Okay. Now, I 1 is the interval where A 1 is suppose A and B 1 is suppose B. Okay. And let P 1 is the middle point of A 1 plus B 1 by 2. Now, if our f of P 1 is 0, then result follows, is it not? Suppose it is not. Suppose f of P 1 is not equal to 0, then either f of P 1 will be negative or f of P 1 will be positive. If f of P 1 is negative, if f of P 1 is negative, then in that case we take the A2 as our P 1, B2 as our B 1, and in case if this is positive, then take the A2 as our A 1, while the B 2 is our P 1, okay, and consider the interval A 2 B 2, consider the interval A 2 B 2 like this, okay. This is fine, and then once one of the case you will be open. So, one of the interval a2 b2 you would have, then find the point p2, which is again the interval half of this, that is basically a2 plus b2 by 2. So, basically this length, when you are taking this a2 by 2, then test the functional value as f2. If it is 0, then result follows. If not, then again either f of p2 will be positive or f of p2 will be negative. So, again continue the same process as above. Okay. So, suppose we are getting after at the nth stage what we get. So, suppose we get the sequence of nested closed intervals a n b n with length such that for every n belongs to capital N, we have the value of f of n is negative and value of the function at the point b n is positive. So, this is the sequence of nested intervals, say a1 b1, then maybe once you divide, here is a2 b2, like this, further divide and like this. So, we get this nested sequence of the nested intervals we are getting, or maybe sometimes here or there, that also possibility may be like this also, that instead of this we get this, or maybe this, and so on like this. So, we get a sequence of the nested intervals which covers the which is contained totally in the previous one, and length of this with the length will be bn minus an an, and that is equal to b minus a over 2 to the power n minus 1. This will be the length of the interval a n b n, length of I n, which is a n b n, this one. Okay. Now, let us see, here we get the sequence n which is less than equal to n which is less than equal to bn, nested interval. Okay. So, what we get it here is, so here we get a sequence of the nested interval a n b n, say I n, such that I1 covers I2 covers I3 and so on, and the finite intersection of I n when n is equal to 1 to r is non-empty. Okay. So, there will be, so by the result which we have, nested interval property, by nested interval property, there exists a point C. That belongs to belonging to I n for all n. This is nested interval property. Okay. So, since for all I n, okay. Now, since C lies between a n and b n for all n belongs to n. For all n belongs to n, we have that 0 less than equal to c minus a n, which is less than equal to b n minus a n, which is equal to b minus a over 2n minus 1, and 0 less than equal to bn minus c, which is less than equal to bn minus an, and which is equal to b minus a over 2n minus 1. This is true. So, when n tends to infinity, this is tending to 0, this is tending to 0. So, this shows limit of an is c, limit of bn is c. So, this implies that as n tends to infinity, limit of an is c, which is the same as the limit of bn. Okay? But f is given to be continuous. What f is continuous. So, continuous at this point, continuous on I, so continuous at c also, which is in I. Therefore, limit of this sequence f of n as n tends to infinity is nothing but the value of the function at the point c, which is limit of f of bn. So, this shows. Okay. Now, further, f of n is always be negative for each n, and f of bn will always be positive for each n. So, therefore, the limit of this sequence f n, which is equal to f c, will be less than or equal to 0, and from here the limit of f bn when n tends to infinity, which is also f c, will be greater than or equal to 0. So, when you take these two together, we get f of c is equal to 0, and that proves the root. This shows c is the root of f. That is, there exists a c where the function will be 0. So, if alternate positive negative, then we can get this thing. So, that is very interesting. It is basically used by numerical methods in numerical to get the approximate root for the function f x equal to 0. Next result which we have, the Bolzano intermediate theorem. Bolzano intermediate theorem. What this theorem says, let I be an interval, I be an interval, and let f, which is a mapping from I to R, is a continuous function, be continuous on I, f be a continuous on I. Now, if a and b, if a b belongs to I, and if k is any real number satisfying the condition, satisfies the f of a is less than k, which is less than f of b, means in between f and f b, we are choosing a real number k. Then there exists a point C in I between a and b such that the value of the function at the point C is k. This is known as the intermediate theorem. Means if f is a continuous function, then it will attain all its values in between the maximum and minimum value. So, in fact, here we are not getting here we are not discussing about the maximum. What we are saying, we are taking two particular values of the function f a and b, f b, and they are distinct. So, if we picked up any number in between f and f b and f is continuous, so there will be some point C available where this number will be attained by the function at some point. So, that is known as the intermediate theorem. So, proof of this is like that. Suppose that a is less than b. Suppose a is less than b. Let us take this one first. Okay, and let g is defined as gx is chosen as fx minus k. So, if we look this function, then clearly at the point a, g a is f a minus k is negative and g of b is positive. So, this function g is a value negative at the point A, positive at the point B, g is continuous function because f is continuous, k is constant. So, addition or subtraction of the continuous function is continuous. So, g is continuous over the interval a b. Therefore, by the intermediate theorem, by the location of the root which we have proved earlier, there will be some point in between a b where the derivative, where the functional g will be 0. So, by previous theorem, that is location of roots, there exists a point C such that with C lying between A and B such that the value of this G C is 0. But what is G C? But G C is nothing but the f c minus k is 0. So, this implies f of c is equal to k. So, there will be a point C available in I where the function will be attained and the k value is attained by the function at this point. Similarly, if we take suppose A is greater than B, second if A is greater than B, then what happens? You consider the function h x. Instead of this we say k minus f x, okay, so that h of b will be negative and h of a will be positive. So, again there exists a point again say C lying between b and a such that the value of h will be 0 at this point, that is k minus f c. So, this implies f c is equal to k, and that proves that. Now, we can extend this result and because this is for any value lying between the two unequal values of f. So, if we replace this f and capital F a and capital F a and f b by its minimum value or the maximum value, that is infimum of this and then supremum of this. If we choose a k in between infimum and supremum, then also we can get the some point value. So, as a corollary to this, we can say let I be a closed bounded interval, and let f is a mapping from I to R be continuous on I. Now, if k is in R, any number satisfying the infimum of f of I, that is infimum of f of I is less than equal to k, which is less than equal to supremum of f of I, that is the minimum value and maximum value. So, k lies between minimum and maximum value, then there exists a number C in I such that the value of the function at the point C will be k, means this k will be attained by the function at some point. Okay. Proof follows just from the maximum minimum theorem and our this previous Bolzano intermediate theorem. So, it follows from use maximum minimum theorem and location theorem of roots theorem. So, what we see here, there exists a point C star, that is, so there exists a point say C star, C upper star and C lower star, okay, in I such that the infimum of this will be f of C lower star. Infimum will attain because I is a closed and bounded interval, f is continuous function. So, infimum will be attained and there exists a point C lower star where the f C lower star is the infimum value, and then this is less than equal to k, which is less than equal to f of c star, which is the same as the supremum of f of I. Now, conclusion follows from the Bolzano relation. So, from Bolzano intermediate theorem, we get a point C belongs to I such that the value of the function at the point C is k follows, and that proves the result, which is now we get one more results, which is also true in case of the continuous function. The transfer of a interval, if f is a continuous function, then it will transform the closed set closed interval to the closed interval. But if interval is not closed, then the image of the interval other than the closed interval, that is open interval or semi closed interval, need not remain to open or semi closed. That is, the nature of the closed interval is only retained by a continuous function, but if the interval is not open and closed, then its nature may change depending on the function. So, we get this result. First, for this first for let I be a closed interval, I be a closed bounded interval, and let f is a mapping from I to R be continuous on I, then the set f I, which is the set of f x such that x belongs to I, is a closed bounded interval. So, proof is just like, suppose m is the infimum value of f I and capital M be the supremum value of f I. Suppose this, okay. Then we know that from maximum minimum theorem, the m n belongs to m n. Now, by maximum minimum theorem, this m and capital M belongs to I, because they exist and there will be a point where it belongs to I. Okay. So, therefore, the every value of f I, moreover, the functional value will lie between the interval m and m, because its maximum value and minimum value only it will be there. So, we can get the maximum value and minimum value, all the values lie in between this. Okay. So, if k is any point, conversely, if k is any point belonging to this interval, then then there exists a point C, k is any value in between m and capital M, then there exists a point C in I such that the value of the function at the C is coinciding with k. It means k is an element of f of I. So, we conclude that any value in between f m is also contained in this. Therefore, we can say m capital M, this closed interval, is contained in f of I. So, combine these two, we get f of I is nothing but m capital M is a closed bounded interval. That is, image of the closed bounded interval under the continuous function is closed and bounded. Okay. Let us see the note. The image of, if f is continuous and I is an open interval, then image of f I need not be open. For example, if we take the say function f x is 1 over x square plus 1 and I is minus 1 to 1, then f of I you can see just half 1. This is not open, closed at one point, not open. Okay. Similarly, if we get, if f is say open semi closed interval, then also suppose I 2 is our interval say 0 infinity, a semi closed interval, and f of x is the same as x square plus 1. We see f of I 2, that f of I 2 comes out to be a semi closed interval, but open at this point. So, what we say I 2 is which is not closed, not a closed interval. Okay. So, if it is not, then we can. So, this shows that. Similarly, third, if we take f x is equal to sin x, and if you choose the interval say minus pi to pi, then image of this interval f I will be the closed interval minus 1 to 1. So, this shows that only the closed intervals under the continuous function remains closed image, otherwise if the interval is not closed, the image of that interval under continuous function need not be the same nature. Thank you very much.